Herkese merhabalar, iyi günler dilerim. Ben İmran Mehmet, British Education Bureau BEB Web'den operasyon müdürü olarak bugünkü yayınımızda sizlerleyim. University of Southampton Webinar haftamız kapsamında düzenlemiş olduğumuz e, yine sıradaki webinarımızda bu sefer Bilgisayar Mühendisliği akademisyeni Profesör David Barry Thomas'la birlikte hem önemli bir konu başlığında hem de üniversite hakkında, üniversitenin bilgisayar mühendisliği bölümü hakkında bilgiler aktarılıyor olacak yayınımızda. Ve son kısmında da sorularınızla ilgili sizlere yardımcı olacağız. Ben sözü akademisyenimize bırakmadan önce çok kısa kurumumuzdan bahsetmek isterim sizlere. Bu arada University of Southampton dünyanın en iyi 80 bilgisayar mühendisliği alanında da İngiltere'nin en iyi 10 üniversitesinden bir tanesi olduğunu da söylemek isterim. Bizler BEB British Education Bureau olarak University of Southampton'ın Türkiye'deki resmi temsilcisiyiz. Temsil ettiğimiz üniversitenin Türkiye'deki tanıtım faaliyetlerine ve bu tür organizasyonlarından sorumlu kurum statüsündeyiz 2002 yılından bu yana. 2002 yılında bundan 22 yıl önce Oxford'da kurulduk ve İngiliz Türk kuruculara sahip bir yapımız bulunuyor. 22 yıldır İstanbul, Ankara, İzmir ofislerimizde, üç büyük şehrimizdeki ofislerimizde öğrencilerimize danışmanlık sağlamaya devam etmekteyiz. Uzmanlık alanımız tamamen Birleşik Krallık ve İrlanda eğitim sistemini kapsıyor. Dolayısıyla bu ülkelerdeki üniversitelerin başvuru süreçleri, sizler için uygun olan kabul şartları, sizin için uygun olan üniversitelerin tespiti, başvuru süreçleri, üniversitelerle iletişimler, konaklama, vize gibi aşamaların hepsinde e, danışmanlık sağlamaktayız. Tüm danışmanlık kadromuz İngiltere ve İrlanda eğitimine hakim olduğu için eğitim sistemine hakim olduğu için bu alanlarda uzman bir kadrodan oluştuğumuzu söyleyebilirim. Birleşik Krallık ve İrlanda'da toplam 150 civarında üniversite bulunmakta ve bizler BEB olarak, web olarak 90'ın Türkiye'deki resmi temsilcisiyiz. Bu doğrultuda da öğrencilerimize az önce bahsetmiş olduğum süreçler boyunca danışmanlık süreçlerini öğrencilerimizle birlikte yürütmekteyiz. Yine benzer faaliyetlerimiz, benzer etkinliklerimiz akademisyenlerle, üniversite yetkilileriyle, öğrencilerle gerçekleştireceğimiz hem yüz yüze hem de online etkinliklerimizi web sitemizden, Instagram sayfamızdan ya da Facebook sayfamızdan takipte kalmanızı tavsiye ediyorum. Ee, İngiltere süreci, Birleşik Krallık, İrlanda tarafındaki aklınıza takılan lisans süreci olabilir, yüksek lisans, doktora, akademik yaz okulları gibi tüm alanlarda ofislerimize bu numaralardan ulaşabilirsiniz. İstanbul, Ankara, İzmir ve Lefkoşa ofislerimize. Ee, Dediğim gibi sunum sonrasında merak ettiğiniz tüm soruları e, chat box üzerinden yazılı bir şekilde ya da el kaldırma butonuyla sesli bir şekilde paylaşabilirsiniz. Sunum sonunda tüm soruları yanıtlıyor olacağız sizler için. Thank you so much, Professor David Barry Thomas. It's yours now.
Okay, let me just share. Okay, so hello, yes, I'm David Thomas. So I'm a professor of computer engineering from electronics and computer science at University of Southampton. So I'm here to talk to you a bit about who we are in ECS, a bit about what we teach, and then how that relates to some of the research that we're doing, because we're quite strong on relating research and teaching. So, oops. So what I'm going to do is talk a bit about who we are and some of the kind of undergraduate programs and master's programs we have. And then, given people are particularly interested in artificial intelligence and things like that recently, what I'm going to do is take a kind of slice through machine learning, covering some of the different research topics that I look at that are kind of related to some of the teaching that we do. So I'll start off by particularly focusing on computer science and artificial intelligence in ECS, but I'll cover the other courses as well. So first off, who are we? What is ECS? So electronics computer science is one of the largest, I I think it is the largest electronics and computer science department in the UK. So we've currently got, I think this is out of date, we've got 125 academics, I think it's more than that now. We have about 1,500 undergraduate students across a number of different programs that I'll cover. And I think that's out of date. We have more than 450 MSc students and a large number of PhD researchers. So there's a large number of people on the academic, student, and research side of things. So electronics and computer science is an interesting school because it covers both electronics and computer science. So it's actually goes back a very long way in terms of where the department came from. So originally it was all about training people to do telegraph for the British Empire. And then over time we developed expertise in things like radio engineering, optical research is still a particular strength. We are one of the few universities still able to make our own integrated circuits, so I'll touch on that later. And in the 80s, we actually merged the electronics department with the computer science department to create this single combined electronics and computer science department. We then had a fire where half the buildings burned down, but we rebuilt, and then we get to now. So this kind of large department covering a large set of areas. Oops. So because we are large, we have a lot of facilities, both in terms of teaching and research. So in terms of teaching, we have a number of different teaching facilities spread across 3 or 4 buildings on the university campus. So we have large teaching laboratories with kind of GPUs available for all desks. We have dedicated software project labs where people do 3rd and 4th year projects. For electronics courses and computer engineering, we have a large electronics teaching lab where students do a lot of practical work. And then there's also hardware project labs for people who particularly want to do hardware-led projects in 3rd and 4th year. But alongside that, alongside the teaching side of things, we also have some world-class research facilities. So, for example, we have the Tony Davis High Voltage Laboratory, where basically people make lightning. There's the Zeppler clean rooms, which I'll touch on in a bit. So that's where we're able to fabricate our own integrated circuits, particularly for research, but also related to teaching. We have one of the largest high-performance compute facilities in the UK, which again is used for both teaching and research, and a measurement laboratory for electronic test and characterization. So in terms of the teaching that goes on here, we've got a large number of courses across CS, AI, electronics, all kinds of different subjects within our research remit. So to give a kind of picture of things across, we are both electronics and computer science, and we have programs that kind of touch on both of these, a bit like we have research that touches on both of these. So on one side, we've got the kind of computer science and software engineering programs. These are computer science, so they are not programming courses. They teach the theory and the mathematics of computer science as well as programming. Then we have specializations, so 4-year master's courses, including specializations in artificial intelligence, cybersecurity. On the electronics side, we have electronic engineering, electrical engineering, and then a number of again, specializations of that for 4-year courses. And then a more general course, electrical, electronic engineering, allows people to kind of like customize across those. We also have specializations in like special programs in aerospace, electronic engineering and mechatronic engineering for people who want to customize in those particular directions. More recently, and part of the reason that I'm here is we've also added new courses in computer engineering, and a dedicated artificial intelligence program, which I'll talk about briefly. And we've also just, well, a couple of years ago, we added a program in biomedical engineering. So you can kind of see that we kind of use the breadth of research and expertise in the department to offer a lot of programs covering different areas. So I'm just going to showcase briefly the artificial intelligence and computer engineering degrees, partially because I'm the program leader for one of them. So these are new programs that we've added that started this year, specifically targeting these kind of more emerging areas. So particularly artificial intelligence as a specialized degree is becoming a thing, and computer engineering, which is better known in North America, is becoming more common in the UK and elsewhere as a kind of recognized program. So just to explain what those are, so computer engineering is kind of what it sounds like. So it's looking not just at computer hardware, not just at software, it's looking at the complete stack of computer hardware, software, and system design. So in computer engineering, it's where people like me would be learning things to design new CPUs or new hardware software accelerators or new artificial intelligence accelerators, that kind of thing. And then artificial intelligence is recognizing that AI has become its own discipline with its own set of kind of required expertise. So that's all about learning how to create the algorithms, create the software and interface with the hardware to kind of create the next generation of artificial intelligence solutions. And something that's become very clear from industry is that computer engineers and AI engineers often work together. So we actually have some explicit aspects of kind of teaching those students together and getting them to work together on projects. So we also have our computer science degrees. So again, just focus on artificial intelligence because people are particularly where we have a steer to talk about artificial intelligence. So as well as the artificial intelligence program, which is explicitly about artificial intelligence, there's also the option to do a 4-year integrated master's in computer science with artificial intelligence, which is a particularly popular option at the moment. Then in terms of taught postgraduate, we also have an MSc in artificial intelligence. So this is like a 1-year master's that covers like foundational artificial intelligence, the kind of core theory of AI, and then provides a large set of optional modules, many of which are actually shared with the 4th year of the integrated masters. So they're our most advanced courses. In terms of employability, I almost forget to talk about these things. So all of our students get employed almost immediately. So we have a huge number of companies who actively come and seek us out, so they tend to come to us for careers fairs that we run. They're very active in recruiting students for internships. So between 2nd and 3rd year of the bachelor's and 3rd and 4th year of the integrated masters, many of our students go and do paid internships. And we're very active in terms of integrating industry into teaching. So, for example, in the 4-year integrated masters, in the 4th year, there is a group design project, and that's actually led by somebody from industry who proposes a real problem for a group to solve. Another kind of somewhat unique thing we have is that Southampton as a university is very effective on entrepreneurship in terms of both academics starting companies and students starting companies. So we actually have a centre called Future Worlds, which is both for students and for academics to actually develop new businesses, and it provides a lot of support in terms of doing that. So that's an overview of ECS and what we are. And hopefully the message comes across that we are a broad department that does hardware, software, particularly artificial intelligence and a number of other things. So in terms of saying a bit more about the types of things that we do, I picked research that I'm involved in that kind of goes across that stack of hardware through to software, and actually touches on a lot of the kinds of things that we teach. So a lot of these things are things that I actually teach at an undergraduate level, as well as doing research in. So just to, this kind of relates to who I am as an academic and where I came from. So I spent most of my career at Imperial College. Like, I was originally a computer scientist, then I started doing research into digital accelerators, originally for computational finance. I was then a research fellow and then an academic there. So during my time there, I moved from computer science to the electronic and electrical engineering department because my research focus changed. I am now at the University of Southampton, so I chose to come here 3 years ago now. And a question that sometimes comes up is essentially, why move? Because I was in a good position, and why did I choose to come to Southampton? So the answer to that is kind of this message, this overall message I think is important about ECS, is the size and scale of the school means that there's a huge amount of research activity going on across lots of different research areas. The size also means we have really good facilities in terms of being able to actually fabricate things like construct devices, measure devices, test things, which is often very difficult within a research context. But it also means that from a teaching point of view, we also have availability of these facilities to integrate into teaching. And then another part of why I came is to actually lead these new programs in artificial intelligence and computer engineering. So I think a lot of the reasons why I came to Southampton is why I think other people should come to Southampton. So in terms of the types of research that I'm involved in, I kind of tried to pick kind of different scales of research, different types of research, running from almost the micrometer scale, like tiny devices that we fabricate, going up the scale through the kind of almost centimeter scale of like individual computers. And then I'll finish by talking about a research project, which is a kind of national scale thing. So in the interest of time, I'm only going to touch on 3 of these, and I am not going to be able to cover these things in detail. I'm just going to try and give a sense of the types of things that we do as research activities, because those also reflect the types of teaching that we do as well. So at the smallest scale, I'm involved in research at Southampton at the kind of micrometer or smaller level. And the kind of research question we're asking is, how much can an individual memristor learn? So not everybody knows what a memristor is. I didn't know what it was until I came here. So a memristor is a type of analog computing component. It's actually, most people know capacitors and resistors and inductors as like circuit components. A memristor is a similar kind of device, but it has different behavior. So intuitively, something like a capacitor, if you charge it up, it remembers how much charge it has, and then it can discharge it. An inductor, if you put charge through an inductor, it builds up a magnetic field, and then it can discharge it. A memristor is a component where if you pass charge through it, it changes resistance and then kind of remembers the amount of charge that's moved through it. So memristors are interesting because they kind of have memory in a way that capacitors and inductors don't. So memristors kind of have memory. They can remember how much charge has gone through them. So quite quickly, people, after the memristor was discovered, people started saying, well, memristors seem a bit like a neuron in the brain. They're a bit like a neuron, because both a neuron and a memristor kind of remember how much charge has passed through them. That's kind of what neurons do. And then you can get both a neuron and a memristor to fire when a certain amount of charge has gone through them. So the research question that I and lots of other people are exploring is essentially, are we able to use these tiny electronic devices, these memristors, to essentially build brains? Like, can we build these devices and get them to learn things? And I was particularly interested in this because we have the Zeppler clean rooms at Southampton. So we can actually go into the lab and actually make these devices, and then so the memristor remembers how much charge has passed through it. That's a fundamental capability of things. The question we're kind of asking or trying to explore at Southampton is, can it remember more than one thing? So like a capacitor kind of remembers how much of an electric field it's built up, but we kind of observed some physical characteristics and said, well, actual memristors that we fabricate have other properties, and they seem to remember not just how much charge has passed through them, they seem to remember something about the pattern of charge that has gone through them. So they're kind of learning more than just a single number. So in collaboration with the SET research group at Southampton, one of my PhD students kind of went into the lab and made silicon wafers full of these devices to try and explore this hypothesis. And surprising thing is that an individual memristor, so one of these individual components like a capacitor or an inductor, can actually learn patterns. So from a machine learning point of view, one of the ways we test this is, for example, with digit recognition, is to take individual columns of pixels from something like a digit, pass that sequence of pixels through a memristor, and after that sequence of kind of ones and zeros has gone through, you can inspect the memristor and then try and infer what was the digit that went through that memristor based on the state afterwards. And this is something you can't do with digital components. You can only do it with analog components. So there's lots of other aspects of that in terms of the maths and physics, but the surprising thing to me was actually one single electronic component can actually remember a surprising amount of information if you present it in the correct way. And so we're actively looking at integrating this into machine learning algorithms at a high level. Then going up to slightly higher scale, Southampton is very strong both in teaching and research on embedded systems. So another research project I'm involved in is the idea of how can you learn things on edge devices when you're extremely constrained in terms of the amount of memory available on the device and the amount of power that's available to supply that device. So edge computing is a relatively recent idea, and the general view of things is that CPUs are now so cheap that we can put them anywhere. Like the cost of a CPU is like cents, if that. So what we can do is put CPUs everywhere because they're so cheap. and embed them at the edge of computer systems so that they process data as it's coming in, rather than trying to centrally process data on a server, for example. So there are some potential advantages here that we'd like to exploit. So a particular thing that we're interested in our research is that if you're able to do learning, for example, on one of these edge devices, you can use it to improve privacy, because it means that human data doesn't need to leave the device and travel over the network. It can stay locally, and so it has privacy preserving properties. Another nice property is that you can potentially have these edge devices keep working and keep doing their function even if the network goes down. But then the big challenge is that these are supposed to be cheap computers, cheap devices. So if you've only got a very simple CPU with very limited storage, if you want to do any kind of machine learning on these edge devices, you have to work out how are you going to remember information about millions of potential pieces of data that you've shown to the device if you've got a tiny amount of storage. And similarly, how do you do that? How do you do learning when you only have tiny amounts of power available at the device? So from a research point of view, I kind of shows the high level view of things. A key question is, if you've got a fixed amount of storage, how can you learn about a potentially unlimited amount of data? So in our work, we've been assuming that there's a fixed amount of storage on the device and that different classes are presented to the device over time. So classes could be something like, in a face recognition system, a class would represent a particular person, and effectively you are presenting new people as they arrive at the system, and you need to remember who that person is based on their face. The difficulty is, as new people arrive over time, you need to make sure that you don't forget about the previous people that you've seen. So this is something called class incremental learning. So the issue is kind of how to decide what information to keep about all of the examples that you've seen. So if we've only got a limited amount of storage, we need some kind of sequential algorithm to process it. So kind of the framework that we have, so over time, we are presenting new classes to the system. And when you present the first class, for example, I present myself to the system and it takes a number of photos of my face, it's relatively easy to decide what to store because you just store all of the pictures of me. The difficulty comes when the next person comes in and we have to make a decision, how many pictures of me do you retain versus how many pictures of the new person do you retain? And based on that, you might end up with a mix. And it might turn out that I am easier to classify, that I'm easier to recognize than another person. And so you might choose an unequal set of examples. And then as time goes on, as more and more faces come along, you have to make decisions about where to spend your storage. So we use something called a genetic algorithm to solve this problem. So genetic algorithm is based on, well, it's based on essentially biological genetics as a way of optimizing things. And so we particularly designed it so that this can run on a tiny CPU. So it can run on a 100 megahertz CPU that's kind of like this size, requires less than a watt. It only has about 1 megabyte of local storage. And what this graph is showing on the left-hand side, this is a fairly standard kind of accuracy trade-off plot that we'd see in both teaching and research. So on the y-axis, we have accuracy. So going from accuracy of 0 means that it can't recognize anything correctly. accuracy of 1 means that it classifies everything correctly. And what we've got on the y-axis here is actually the proportion of examples, or the proportion of faces that we're able to retain on the device. So as we go in this direction, this means that we have a smaller and smaller memory, and we can hold on to less and less data. And then these two comparisons here, this line here represents the accuracy that you get for a particular retained subset, so for a particular memory size, if you kind of just keep them at random. So if you just say, well, I've only got space for n samples and I have m samples, I need to throw away some fraction of them. This curve up here shows the accuracy that we get if we optimize the set of samples on the device. So even though it's a very simple low power device, we can still run some algorithms. And in terms of reading this, if we take the smallest amount of memory, we see that if you do this naively, you get less than 50% accuracy, which is just not useful. It's not always worse than chance. Whereas if you apply our algorithm, you get something close to 70% accuracy, which in many situations is enough to be useful. So by thinking about algorithms that can run on the hardware itself, we can do this kind of intelligent subset selection without having to communicate with a server, and so maintaining privacy of the system. So the final thing I selected is actually an ongoing larger research project. So this is where we go up the scale again from essentially to cloud scale machine learning. So in this case, it's kind of a global computing, because the computers can be anywhere, with the idea of estimating national financial risk. So I've kind of deliberately chosen some things that go from like very simple and very tiny up to kind of much more abstract things. So this is a bit more on the computer science side of things. So this is an example of funded research, of which we have a large amount going on at Southampton. So essentially it's where we've gone to the research councils and pitched a particular research project, and then they've allocated funding to us. So in this case, it comes from something called EPSRC, which is a UK funding council. And this is actually like a 5-year project with £7 million across 3 universities. So as with ECS itself, we have a lot of expertise within this project. So just within the Southampton component of this, we have theoretical computer scientists, we have machine learning people, we have people who know about hardware accelerators. And this kind of funded research project is really good for collaboration, not just between universities, but it's also something we use to kind of collaborate with students in terms of things like MSc projects and third-year projects. So this is a nice opportunity to get students involved in active research. So the kind of thing we're trying to solve with these big projects is we kind of try and pick some big challenge and some big opportunities, and then work for 5 years to try and actually solve this. So in this particular project, this is a case where we've been looking at what do we think next generation artificial intelligence is going to look like. So we currently have convolutional neural networks, tensor processors, that kind of thing. But there's a question of what comes next. There's also a computer science challenge of, we have lots of CPUs and GPUs and things in the cloud. Part of the difficulty is actually programming them and managing them if we want to use millions or billions of CPUs in the cloud. And the driver that we chose for this is, because you've got to think big, is trying to evaluate the financial risk of the entire UK essentially in real time. And as a research project, again, it's going to build on, I think, strengths of ECS, because it involves a lot of different areas of hardware, software, machine learning, computer science. So I give a kind of very rough idea of what we're trying to do. So this is an ongoing project. This is something that started a bit less than a year ago. So kind of the type of machine learning that we teach right now tends to be fairly regular. So we teach third and fourth years, or even second years these days, how to do things like image recognition. But a lot of those things are based on GPU optimized algorithms. They're based on black box algorithms like neural networks, where they make classifications, but they don't make very sophisticated classifications. And they quite often assume that you're going to do one very, very intensive learning step, and then the learned model is going to stay the same. So what we're interested in terms of next generation machine learning is, firstly, the input data comes in lots of different forms. So there might be images, there might be tabular data, there is time series data, there are textual sources like news sources, that kind of thing. The relationships between these data are much more complicated than traditional image processing or even text processing. So we need to extract relationships between and within all of these different data sources. In terms of computation, we have to move beyond just CPUs and GPUs, because we're not going to get the power efficiency that we need from the systems. So we need to be able to create machine learning systems that are able to exploit all kinds of different compute infrastructure and map them onto the right device for the type of learning. And from an end user's point of view, what people really want is kind of better answers from machine learning. They want to know, why did a particular decision get made? Like, why is a particular classification made? They want to understand the relationships with the input data rather than just getting an answer. So we think we can do all of this using a computer science abstraction we developed internally called event-triggered computing. So this is something that we are actively building. So the reason we chose financial risk is because this is we want to solve big problems that are important to lots of people. So we chose financial risk because if you look at the way that we try to manage financial risk at the moment, not just in the UK, but in almost every country, the primary way of doing this is called stress testing. So that's where, say, the Bank of England comes up with a really bad financial scenario, like interest rates go up by 10%. And then they say to each institution individually, if this scenario happened, how much money would you lose? But they do it individually for each institution, so they don't know anything about the correlations between how much the institutions might lose together. It would be attractive to try and do stress tests on all of the positions that all of the institutions have. Like, it'd be nice to collect all of the stocks and shares that everybody owns and then do a risk analysis on that. But that's just infeasible. Well, it's not billions, there are trillions of individual stock positions and foreign exchange positions that institutions have. And it would just be impossible to collect that data, let alone process it. So what we're doing is an example of kind of like advanced applied machine learning, is trying to build this picture using machine learning rather than trying to do it all using simulation and stress testing. And so we're developing next generation machine learning to look for these patterns, and then these kind of advanced cloud computing abstractions to actually run all of them. So just as an example of roughly what this looks like, I can't really go into detail. Some of the techniques we would use include things like extracting time series data. So these could be stock prices or volatility indices. We then use signal processing techniques, kind of from electronic engineering, in order to smooth those things, and then apply machine learning techniques to actually identify interesting turning points in the smooth data, and then turn it into individual frames of data that we can learn on. Once we've done that, we can actually train our kind of advanced machine learning algorithms to actually analyze those frames and come up with a model of those time series right now. We can then use those to do real-time forecasts, so something called nowcasting, like what does the scenario look like now, in order to come up with possible futures based on this model. And we can then use that to understand what might the economy do tomorrow? What is the distribution of things that it might do? So obviously there's a lot more going on in there, but this is an example of the type of large-scale research project that we do at Southampton. And we do actively try and get, well, we do get undergraduate and master's students involved in this project. So I think that's quite a nice opportunity. Okay, so in conclusion then, so essentially what I've been covering is like electronics and computer science at the University of Southampton. And I think that the kind of key advantages or the key attractions for me, and I think for other people, are the breadth and scale of electronics and computer science, which is important both for teaching and for research and the interactions between them. So this doesn't mean that because we have lots of students, all of our classes are huge, because we have a large number of programs that are specialized in these particular areas. So the cohort sizes aren't too large. And we have a lot of staff to actually do the teaching. Our staff-student ratio is actually quite good. And I think this scale is really nice in terms of being able to just do lots of different types of research and teaching. So we can create our own chips. That's something that we can do in-house. We do a lot of embedded systems work, both in a research context and a teaching context. And we have compute infrastructure. So this is Redis compute infrastructure that allows both staff and students to actually make use of kind of large-scale computing on demand. So, for example, we have a large number of H100 NVIDIA GPUs, which I think are online now, which are available to students as well as staff. So yeah, I will stop there, and yeah, I'm happy to take any questions.
Thank you so much for the all information, Professor David Thomas. I can let them know that they can share the questions in Turkish as well. Sorularınızı merak ettiğiniz hem konuyla ilgili hem de üniversite hakkında, bölüm hakkındaki sorularınızı paylaşabilirsiniz chat box üzerinden veya sesli bir şekilde. Southampton Üniversitesi hakkında çok kısa bir bilgi de vermek isterim. Bu sene itibarıyla University of Southampton lisans programlarına başvurularda lise diploması da kabul etmeyi başladı. Dolayısıyla yani bu yıla kadar uluslararası bir diploma şartı aranıyordu başvurularda, IB, A-Level gibi. Lisans programlarının başvurularda bu sene itibariyle Anadolu Lisesi, Türk Lise Diploması, MEB diploması da kabul edilmeye başlandı. Bu güzel gelişmeyi de paylaşmak istedik sizinle. Bununla birlikte hem lisans hem de yüksek lisans özelinde burs imkanları da sağlayan bir üniversite. %100 bursa kadar sağlanan destekler söz konusu. So we already have one question. The first one is as a hyperactive person, I have a question whether or not teachers will be helpful.
Sorry, what was the question?
As a hyperactive person, I have a question whether or not teachers will be helpful for me, like whether they are helping the students in general?
I mean,
Please
in
have a look.
terms of student support, so in terms of the talk component, we have, alongside lectures and those kinds of things, we have laboratories which have both academics and PhD demonstrators there to kind of answer questions and help out. And we have personal tutorials where each student has a session with a personal tutor each week to kind of either talk about technical content from the subject or to help out with pastoral care. I mean, in terms of things like if there are particular, if students need particular adjustments, we also have a formal support process for things if people need particular types of assessments or if they need extra time on exams, those types of things. So there's a standard process if people need extra assistance for particular reasons. That's applied at university level and will then be fed through to all kinds of assessments.
Okay, thanks so much. The next question is about the entry requirements for the master's degree courses. Would you like to provide information, or I can also let them know?
To be honest, the master's degree courses, I don't know the entry requirements because I'm involved in admissions on undergraduates, but I'm afraid I don't know specifically for masters.
Yeah, I can explain in Turkish in that one. Program bazlı baktığımız zaman birçok aslında master programı mevcut üniversitenin Bilgisayar Mühendisliği bölümü özelinde. Dolayısıyla giriş şartları olarak tabii not ortalaması ve IELTS şartı şeklinde öne çıkan giriş şartları söz konusu. Burada tabii yani not ortalaması bazlı 3'e yakın bir not ortalaması şartı aranıyor genellikle Southampton'ın master programları için. IELTS'ten de 6,5 şartı arandığını söyleyebilirim. Yine ben mail adresimizi sizlerle paylaşıyor olacağım chatbox üzerinden. Görüşme, webinar sonrası giriş şartları ile ilgili daha detaylı görüşmeler sağlayabiliriz. So the following question is...
Imran, sorry.
Yeah, sure.
I'd like to say a few things as well in regards to, obviously, thank you, Professor David Thomas, for the informative presentation and BEB for organizing. In terms of postgraduate degrees, our entry requirements vary between a first and a 2-1. A first means an excellent GPA in Turkey, a 3.5 and above, or a 2-1, which is a 3.0 and above, in order to be eligible to apply for any of our courses and get an offer. In addition to that, English language, if you can prove that you've been taught and assessed in English in the last 2 years, you wouldn't need to provide an English language test, but you may need to provide English language qualification for the visa. Now, in terms of scholarships as well, we offer scholarships both at the undergraduate and postgraduate level. The information is available on our website. But then this is a new development that we do accept students from the Turkish lycée directly onto year 1 into any of our undergraduate programs in ECS, so computer science, EEE, and many other programs. So that as well is a new development. It's new for this year. We weren't doing it last year, but this year onwards, if you are from an approved school in Turkey and BEB can provide you with that information, you are eligible to come onto year 1 straight away. Thank you.
Thanks so much, Rami. The following one is about fabricating our own device. Could we design and generate our ASIC or IC chips for master projects?
So certainly you could design one. The issue with getting it fabricated within the time frame of a master's project is that fabricating actually takes quite a long time to kind of get the mask done and to book time. It is feasible, particularly if you, sometimes people fabricate chips because they do a master's project attached to an existing research project. In terms of like a full ASIC, there are limits on complexity of the ASIC. So, you know, if you want to do like a GPU as an ASIC, then that kind of takes too long, it's too costly. But people do simple devices to explore particular research questions. It does require talking to the supervisor to make sure that all the timeframes line up, though. So it's feasible, but it requires quite a lot of attention to the project management side of things.
Thank you. Would you explain the image includes the classes Q1, Q2, and Q3 are stacking and passing as an argument to next function? It was in the embedded CPU slide.
So this one?
Yeah, Q1, Q2, and Q3.
So sorry, what was the question again?
Would you explain the image includes the classes Q1, Q2, and Q3 are stacking and passing as an argument to next function? It was in the
Oh, I
embedded
see.
CPU slide.
So essentially these arguments here, yeah. So Q1 rep is kind of an indicator for the particular class. So it's almost like the label for that particular class. And then we're using D superscript to mean the original full data set for that particular class. And then this represents what we've retained for that particular class. So in terms of then the way that the functions work, I mean, this is quite an abstract view of things. This is an input which represents the data. This is what's called a hyperparameter, which gives particular parameters about the learning method. And then, yeah, it is then like a function, a chain of function calls going round where, yeah, this data gets input here. So I chose like an ultra abstract image here, so maybe, I'm not sure how clear that is.
Thank you so much. There is the question in Turkish. I can explain it for them. Bilgisayar bilimleri ve bununla alakalı ya benzer programların yüksek lisans başvuruları için şartlar değişiyor. Programdan programa değişiyor ama bazı programlarda minimum 3, bazılarında ise 3,5 olacak şekilde şartları, giriş şartları, ortalama şartları söz konusu. Bizlere dediğim gibi kabul şartları ve başvuru süreçleriyle ilgili ulaşabileceğiniz mail adresini ben biraz sonra chat box üzerinden paylaşıyor olacağım. Another question is also about the entry requirements. Can someone from another department also take these courses?
Oh, so another department within Southampton. Usually not. So there is sometimes the ability for students in other departments to do third and fourth year courses from another department. There is limited ability to do that. So, for example, students within ECS have limited ability to do a certain subset of courses from elsewhere when it's quite relevant. A few students are able to take some of the ECS courses. So, for example, students from from engineering at Southampton are able to take some of our courses like robotics, but generally speaking, the options available within ECS are really only for ECS, and it's more the exception that you can actually study third and fourth year options in other schools and departments.
So much. these are the all questions so far. We can maybe wait for a couple of more seconds. Yeah, there is one more question. You showed the handwritten 0 digit in previous slide, and it was processed in columns as far as I understood. However, sequential models are accepting data in linear sequence as I remember. So I am confused about how the image is processed as column.
Yeah, so that's one of the kind of slightly odd things about this way of processing things is that, yeah, it's kind of split into columns. So you're kind of taking columns from the image and then using that as input data. So it's kind of not shown here, but what we'd do is potentially have one of these memristor devices processing each of the columns, and then each of those devices is kind of like seeing a different column go past and remembering something about the pattern and the ordering of the ones and the zeros. So any individual column is not enough to be able to say what digit it was. But if you get the kind of the memristor states from each of the columns, the combination of those states is often enough to be able to tell what the original digit was. So this is it's actually an example of something called reservoir learning, where you have a complex nonlinear reservoir of computing, which hopefully transforms the input image into a very different space. And then in that very different space, you can actually recognize, more easily recognize the digit. So you're right, it's each individual column doesn't tell you enough to get the entire image. But if you look at multiple columns, there's often enough information across the columns to actually recognize the digit.
Thank you very much. Rami, would you like to share your email address as well? Yeah, there is one more question, I think. Is there an article on ML and AI that graduate students can get involved in? I want to get study about this thing, but I don't want to drown in math.
Sorry, say that again.
Is there an article on ML and AI, machine learning and AI, that graduate students can get involved in? I want to get study about this thing, but I don't want to drown in mathematics.
I'm not quite sure what you mean by article, like a news article or a
Kind of project, I think, is
a project. So a project before doing a degree, or I mean, certainly within a bachelor's or a master's, there would be the ability to do a project in artificial intelligence. I think there was a comment about maths. Unfortunately, this does all involve a lot of maths. I wasn't quite sure what the question was. So there are, I mean, any of these degrees requires students to be good at maths. Artificial intelligence, there's the opportunity to do projects more on the applied side of things, where the mathematical component is kind of more hidden within the tools, or there are people who do like master's projects in theoretical machine learning or theoretical artificial intelligence, where they're actually kind of creating the new maths for other people to then use. I'm not sure if that's answering it. I can clarify if there's any follow-up.
Thanks so much. I think we covered all the questions. Thank you so much once again, Professor David Thomas, for your time and all the information you provided, and also Rami for your participation and support as well. We hope to see you in Turkey face to face as well in the near future.
And Ran, I've just seen one question pop up
Yeah.
very quickly. What available scholarships are there for us to apply to for this graduate course? At the postgraduate level, we do have a few scholarships, but the main scholarship, which is guaranteed for every postgraduate student from Turkey, is a 2,500 excellence scholarship for Turkey. So that's guaranteed in addition to what the faculty offers as well. So Imran, if you can follow up on that and share our website with our scholarships to Kaila, then we can see how we can help.
Yeah, we will contact them after the webinar. For sure.
Sorry about the noise in the background. I'm at the airport, just boarding a flight to on university business. So thank you very much, David. Again, thank you, BEB, and everyone who's attended. And hopefully we'll see you soon.
Yeah.
Thanks so. Have a
Thank
nice
you,
day.
everybody, and yeah, have a nice weekend. Bye.
Thank you. Have a nice. Bye bye.